All right, let's get into it. Today, we're going to build the ultimate math toolkit for physics. We're breaking down the 3 absolute must-have concepts you need to not just get by in physics, but to actually understand how the universe works.
You ever open a physics book and just feel this wave of math anxiety wash over you? Yeah, that feeling that you've accidentally wandered into an advanced math lecture? Totally normal. You are definitely not alone.
Well, here's the secret. You're not wrong. Physics really is a language, and that language is math. But, and this is the good part, you don't need to be a math wizard. You just need the right toolkit, a couple of really powerful ideas that unlock pretty much everything.
Okay, so let's grab our first tool. This is the foundation for, well, everything else. It's the language we use to just describe where stuff is and how it's oriented in space. We're talking about geometry and trigonometry.
So what do we do with this? Well, think about a simple block sitting on a ramp. Geometry helps us map out its position, and then trigonometry, that's the magic that lets us split up the force of gravity into pieces, one part pulling it down the ramp and another part pulling it into the ramp. It's basically the blueprint for any physical situation.
And you know what's at the heart of it all? A formula you've known for years. A really great tip from the source material is to just memorize some common Pythagorean triplets, like the 3, 4, 5 or the 7, 24, 25 triangles. You see these ratios pop up all the time, and knowing them by heart can save you a ton of calculation time. It's a fantastic little physics shortcut.
And of course, you've got the big 3, sine, cosine, and tangent, SOHCAHTOA. These simple little ratios are the absolute building blocks for figuring out any angle or breaking down any force. You're going to use them everywhere. Okay, but here's the catch. Geometry is great for describing a snapshot in time, right? But the universe isn't a snapshot. It's constantly moving, constantly changing. So to capture that motion, to describe how things move, we need a more dynamic tool. It's time to bring out calculus.
Now, don't let that word scare you. A derivative, at its core, is just a tool for finding how fast something is changing at one specific instant. Think of it like this. It's the slope not of a whole straight line, but of a curvy graph at one single tiny point.
This graph from our source material shows this perfectly. Look at point 1. The curve is really steep there, right? So it has a high derivative, a high slope. Then as we move along to point 2, it starts to flatten out, so the derivative gets smaller. By the time we get to point 3, it's almost level. The rate of change at that instant is practically 0.
You know, calculus has these 2 sides, and they're perfect opposites. The best way to think about it is your car's dashboard. Differentiation is the rate finder. That's your speedometer. It tells you your exact speed right now. Integration is the total finder. That's the odometer. It adds up all those little instantaneous moments to tell you the total distance you've gone. 2 sides of the exact same coin.
So let's put this tool to work with a problem from the source. We've got this metal disk. It's being heated, and its area is growing according to this formula here. Now we want to know how fast it's growing at one specific moment. So we apply our differentiation tool, and that gives us a new equation for the rate of change at any time t. Simple as that.
And, just to complete the picture, integration does the exact opposite. If we already knew the rate of change at every single moment, integration is the tool we'd use to add up all those tiny changes to find the total area, or the total distance traveled, or the total work done.
All right, time for our third and final tool. This one adds a super crucial layer of information, because in physics, just saying how much isn't always enough. A lot of the time you have to ask, okay, but which way?
And this brings us to the huge difference between scalars and vectors. A scalar is just a number, a magnitude. Think mass or speed. But a vector has both magnitude and direction. Force is the perfect example. It always matters which way you're pushing.
And this is where things get really interesting. In the world of vectors, the normal rules of math that you've known your whole life, they don't always apply. Adding 10 and 5 might get you 15, or it might give you something totally different.
This table, which is based on a few questions from our source, shows you exactly why. Let's say you have 2 forces, one of 10 newtons and one of 5. If they both pull in the exact same direction, yeah, you get 15. But what if they pull in opposite directions? They partially cancel each other out, and you're left with only 5. The final result depends entirely on the angle between them.
So, what officially makes something a vector? Well, this quote from the source material nails it. A vector isn't just something with direction.
It's a quantity that has to follow a very specific rule for how it's added, what we call the triangle law. It's like the official test for being a vector.
And just like that, we've done it. We've gathered the 3 essential tools for our physics toolkit. So now let's lay them all out on the workbench and see what we've built.
So here it is, your toolkit in a nutshell. Geometry and trig, you use those to describe the setup, the blueprint. Calculus, that's what you use to analyze how things are changing. And vectors, you pull those out whenever direction is a critical part of the story. With these 3, you are ready to tackle almost any problem physics can throw at you.
So I'll leave you with this question to think about. After seeing how these tools work, do you think math is just some annoying hurdle you have to jump over to get to the real physics? Or is it something more? Is it the actual language, the very grammar, that lets us write down the rules of the universe